Okay. So we talking about thermochemistry. Chemistry is looking at how chemicals and molecules interact, right? Well, a very common compound that we have here on this planet is dihydrogen monoxide, right? We call it water. I know, mind blowing. Water. Water is very interesting when it comes to chemistry, and more specifically thermochemistry, for a few reasons. Okay? Water molecules are pretty unique, and we'll talk about how they function in greater detail later, and a little bit why they do some of the things that they do. But there is something in connection with thermochemistry, which again is just kind of the study of how heat and chemistry are connected, right? So thermochemistry, the study of heat in chemistry. All right. There's a very important concept in thermochemistry that is called specific heat. Just kind of a continuation from last time. Yep. Specific heat, right? Specific heat is the amount of energy needed, and we're going to use a unit called joules for the energy. It's also just an uppercase J, all right? Needed to increase 1 gram of a material increase 1, let me see here. Increase 1 gram of, increase, I guess you could just use heat there, I don't know. By 1 degree Celsius. I don't know how much that makes sense. Increase heat, or add heat, I guess. Increase heat. There's a word that I'm looking for here, and it's probably just heat, but you get the gist, right? It's how much energy you have to put in to make something 1 gram of something 1 degree Celsius hotter. Yeah? I mean, it kind of makes sense. It's definitely not the perfect definition, but we use a specific unit for specific heat. Gosh, I'm going to use the term specific a lot today. It's kind of like literal. Like, I'm literally, like, so hot right now. Now, okay, we use the unit of joules per gram Celsius. And I know that sounds like a very confusing unit. It's not that bad. Joules per gram Celsius is just how much energy for 1 gram by 1 degree Celsius. Does that make sense? Okay, we'll look at some things, okay? And why do I mention water? Okay, why did I mention water? Well, water has an unusually high specific heat. okay, has an unusually high specific heat. That's not how you spell specific. Specific heat. Okay? Pacific heat. No. It's the Pacific heat of the specific heat. The specific heat of the Pacific. All right, anyway. And so to give you a couple examples, we'll do water. Okay? The specific heat of water, and you don't need to memorize this, like these numbers. I will always give these numbers to you, okay? The specific heat of water is, this is liquid water, okay, is 4.18 joules per gram Celsius. Okay, and that probably doesn't seem very high, but for instance, gold, pure gold, has a specific heat of 0.12, or actually 0.13, we'll round up. 0.13 joules per gram Celsius. So water is a lot higher, right? What does that mean? What, in terms of specific heat, what does that mean about water versus gold? What do you think? Is it harder or easier to heat up water? Hannah? It's harder to heat water than gold. Pretty interesting, right? What about paper? Like just literally a piece of paper. Do you think it'd be easier or harder to heat up paper versus water? Easier, right? You'd think that. Why? Why would you think it'd be harder, Franklin? Paper is not, the paper shouldn't have too much water. It might have a little bit.
I know, not
A little bit goes a long way. Okay. So some people are saying it's harder to heat a paper than water. Emma, yeah? At a certain point, it just gets too hot and lights on fire. Yeah, that is true, but it's it does light on fire. But the truth of the matter is that it's actually much easier to heat paper than it is to heat water. The specific heat of paper is 1.37. No, sorry, 1.34 joules per gram Celsius. Okay? So water is not quite 4 times, 3 times more difficult to heat than paper. It takes more energy. Okay? Water actually has an extremely high specific heat, and we'll get into why that is when we get to intermolecular forces. But what I want you to know right now is that it's difficult to heat water in comparison to other things. And when we're doing experiments and so forth to see how energy flows, you'll notice that you need to heat pure water longer over the same heat source than pretty much anything else to increase its temperature. Okay. This is, for instance, when you're making yourself some mac and cheese, right? You put the water in a pot. Okay. If you put the pot on your stove, you turn the stove on, turn on high because you're hungry and you want to make yourself some mac and cheese fast. If you put your finger in the water, your finger is going to be good for a while. But if you put your finger on the outside of the pot, your finger's going to burn quickly. The pot is going to get hot fast. The water takes a while. Okay? This has big implications for like the climate here on Earth, and why certain places are cold and why certain places are hot. Really what it means is that people that live near oceans have an unfair advantage because the water is warmer in the summer and colder in the winter, and so they have mild winters and cool summers, and they're cheating. So, like, I was looking at the average temperature of Manchester, England the other day. In the winter, as one does, like in the winter, their average temperature is something like 6 degrees Celsius. Our average temperature here is like 1 degree Celsius in the winter. And their average temperature in the summer is like 22, and ours is like 30. So we have hotter summers and colder winters. Cool. Anyway, cheating. They're cheating. That's what they're doing. Anyway, so specific heat. Well, what does that mean? What does that mean? Well, what's cool is that we can calculate. It is cool. We can use the specific heat of water, which again is 4.18 joules per gram Celsius, and we'll put that on this slide here. 4.18 joules per gram Celsius. Okay. So let's just say that we have a 1 milliliter thing of water. You have an extremely small amount of water in like a dropper or something like that, okay? 1 milliliter of water. All right. Here's what's so great about the International Standard Unit. Remember that 1 milliliter of water, do you remember what the mass to volume conversion is for water? You may not, it's okay. It's 1 gram. Isn't that great? So great. Imagine if you had to convert between teaspoons and ounces. It makes me vomit just thinking about it. Okay, but we only have to convert between milliliters and grams, which for water, it's 1-to-1, which is fabulous. Okay? So if we want to increase the temperature of this 1 milliliter of water, how many joules do we need to add into the water if we want to increase it? Let's say that it's at nice room temperature, 20 degrees C. If we want to get it to, if we want to get it to 21 C, how many joules do we need to add? Vince? Yep. Beautiful. We added 4.18 joules, and now our water is 1 degree Celsius warmer. Okay? Pretty cool. All right? Now, what if we wanted to increase the temperature of this 1 milliliter of water from, now that it's 21 degrees, what if we want to increase the temperature to 45 degrees? Now, let's go, how about 37? Maybe we want it to be nice and toasty. 37 is like a good hot tub temperature. All right. Again, this is only 1 milliliter, so the only thing that'd be taking a hot tub bath would be like an ant. Okay. In this 1 milliliter, how many? Oh, that's not okay. How many joules do we need to add to this water to increase its temperature from 21 to 36 or 37? How would we figure this out? Brendan?
Well, first we have to minus 37 from 21.
Okay, which is what?
16.
16. So we're increasing the temperature by 16 C. Okay.
And then times it by 4.18.
Yep.
66.88.
So let's just review on how we did that. We took our desired change in temperature, which is 16 degrees Celsius, and we are going to multiply it by the specific heat, which is 4.18, to give us, what was the answer?
66.88.
66.88. Joules. Okay? Do we see how that works? Now, let's say that we actually want to heat up the water so we can, you know, take a swim or whatever, okay? We're going to need a lot more than just a milliliter, okay? Well, let's not get to that one yet because that'll take liters. But what if we want a hot cup of coffee? There we go, hot cup of coffee, right? And we have room temperature water. I'm going to copy that and make a text box and paste and make it bigger. Okay. So we want a cup of coffee. Let's say that it's my handy dandy student tears mug with coffee. This is probably I don't know, 350 milliliters, something like that. Okay. So 350 milliliters. Right? Which handily is how many grams? It's 350 grams. Okay? So we've got 350 grams of water. We want to, it is currently at 20 degrees Celsius because it's just been sitting. And I want to get it really nice and hot. Cup of coffee, let's say it's, my desired temperature is 88, okay? Let's do this, okay? 88 degrees Celsius. Maybe that's like my perfect cup of coffee temperature, all right? Not boiling, but really, really toasty. Warms up my hands when I hold on to it. Yeah, Emma? Oh, that was just that's just the temperature of the water right now. 20 Celsius is room temperature. Okay, 20 Celsius is room temperature. 88 is what I want it to be. I want it nice and hot. Okay. So that is a change. The difference between those two is how much? 68 degrees, right? It's a change of 68 degrees. So the question now is, how am I going to figure out how many joules of energy we need to put into the water if we want to change it that much? What do you think, Franklin? If we have 350 grams of water, it's going to take a little bit more energy than just 1 gram, right? Okay. So here's what we can do. Here's what we can do. We can take this and see our unit here. We can manipulate this unit. If we do 4.18 multiplied by 350, that'll give us, I'll do the math here for you, 4.18 times 350. That gives us 1,463. And the new unit that we can use is joules per 350 grams Celsius. See how we did that? Now we figured out how much energy it takes to heat my cup of coffee, my cup of water, by 1 degree Celsius, right? Because it's not 1 milliliter. A 1 milliliter cup of coffee isn't going to do much for you. Debatable. It depends on how strong the coffee is, I guess, right? Ultra caffeine.
60 hours.
It's just a single milliliter of caffeine. Like that's all it is caffeine. There's no water. just deep in it. Okay, so it takes 1,463 joules to increase the temperature of my mug of water by 1 degree Celsius. So we can just take that same number, 1,463, and we can multiply it by our desired change in temperature, which is 68. Which gives us 99,484. And that is joules. Did you get the same answer?
Yeah.
Then that's fine. Did you multiply it by 68 and then multiply it by 350? Yep. Good old multiplication, it's commutative. So you can just go wherever you want. Okay? Do we see how we did that? More or less. Yes? Cool. Okay. We will solve. So we've been solving for joules, right? We've been solving for joules. So now let's solve for something else. Can I copy this? No, I can't. Okay. Maybe, there we go. Okay. So if we've been solving for joules, and let's say we know that we have a can of propane, okay? And I'm not going to give you we'll talk about enthalpy in a little bit. We have a can of methane, all right, which for like a cooking stove. And we happen to know that that can of methane has 35,000 joules. All right. 35,000 joules. And we have a 500 milliliter bag of water, which again is equal to 500 grams. That's a G. There we go. All right. What we want to figure out is how much can we heat up our bag of water? How hot can we get it? How hot can we get the water? So how are we going to do this? Oh, Franklin's onto something. So if we take our specific heat, 4.18, and we multiply it by 500, so 500 times 4.18 gives us 2,090. And our unit is now joules per 500 grams Celsius. That's a unit, okay? This is a unit. What that tells us is we need this many joules to heat our bag by 1 degree Celsius. Very good, Franklin. So what we need to do is we know that we have 35,000. We know that we have 35,000 joules, right? If we divide that by the specific heat of our bag of water, which is 2,090 joules per 500 grams Celsius, that will give us, so let's see here, 35,000 divided by, that gives us 16.7 degrees Celsius. So we can heat our 500 milliliter bag of water by 16 degrees Celsius. Do we see how that works? Yes? Cool. Wait, what?
How many joules is like a normal propane can, I guess?
A lot more than 35,000. A propane can, like, that you would buy at a outdoor sporting goods store, would probably have a few million joules of energy in it. Yeah, these are really small numbers that we're dealing with, just so that they don't scare you. Yeah, this would be maybe 3 minutes of gas. Okay. Yeah, Vince. 100 million in a gallon. So for gas, so 100 million. Yeah. So you would need. So you can look up the heat that will be released when you burn methane, and we'll get to that in a little bit. Okay. Questions on specific heat so far? No? All right. Let's say that we want to light some paper on fire. Cool. We want to light some paper on fire. The thing is that paper is quite light, right? Paper has a specific heat of 1.34 joules per gram Celsius. And we just have a single piece of paper. A single piece of paper might weigh 0.3 grams. And in order to get it to ignite, we probably need it to get to, so we'll do room temperature again, so 20 degrees C. And we need to get it to 300 degrees C, which is a difference, a change of 280 C. Okay? All right. So, how are we going to do this? How do we figure out how much energy is needed to light this piece of paper on fire? What do you think, Brendan? What do you think? How are we going to get this?
Okay. Is that 0.3 grams? How many grams?
The paper is. Yep, the paper is 0.3 grams.
It's at 20 C, 1 get 300 C, 280 C. So let's see. So first, so we have the two. So let me just check. Would we times it by the 1.34 280 by 1.34 and then divide it by 0.3?
We don't have to divide by 0.3. We actually just multiply our numbers together again. So if we multiply that by 1.34, then that gives us 0.402 joules per 0.3 grams Celsius, right? And how much do we want to increase the temperature by? 280. So 0.402 times 280, which gives us 112.56. Okay? So we don't have to add in very much heat to light this on fire. Okay, that's where I'm going to stop the video on specific heat. Like and subscribe or whatever.